today's discussion and lecture is the subscribers loop design. What is a subscribers loop? It is the physical link that connects a subscriber or the customer of a telephone uh, exchange, um, and the link that connects that customer to the telephone exchange. All such circuits, whether they are made up of um, a copper wire or an optical fiber, it would be called a subscribers loop. When we talk about a PSTN number, or the public switch telephone number, uh, we are basically referring to the local loop numbers. For example, the numbers that we have from PTCL in Pakistan. So the line that connects our telephone set to the telephone exchange, it is called the subscribers loop. And this link, this wired link, does need a lot of design also. Let's see what are the different parameters that bound us to to design it in a certain way. First of all, let's see if we have a local network, what is the percentage of investment involved? For a local loop, 50% of the investment goes into the local loop for a local network, which includes the telephone exchange and its inside plant, and the cables and the trunk plant that connects different exchanges. If we club everything all together, then 50% of the total investments go into the development of the subscribers loop. Now you can see in this sample local area in which an exchange uh, is started. We can have rural concentrators over here, and we can have toll connecting trunks, and these are heavy urban area concentrations. These are rural satellite exchanges. So in this way, telephone exchanges are connected together. More exchanges are required for the congested urban areas. Restraints for local loop design. First of all, the geographic extension of the local area of interest is important. The number of inhabitants and existing telephone density has to be taken care of. Calling habits have to be seen, because in some areas the number of calls initiated and the length, or the length of the calls is larger as compared to the others. Similarly, the percentage of business telephones would incur more traffic to the area. Now, the location of the existing telephone exchanges has to be taken care of, and we have to see if that particular telephone exchange can handle all the customers or not. If the distance is too much, and there's a large number of customers demanding new connections, then a new telephone exchange would be set up. Then we need to see the trunking scheme also, and the trunking scheme shows the number of trunks connecting a particular exchange with its neighboring exchange. Now, it's not always like that. Being all the exchanges connected to being connected to all other exchanges in the city. It's not like that. There is a tandem exchange in a city which connects all the telephone exchanges. And when one telephone exchange wants to connect to another telephone exchange, it has to go through the tandem exchange. And the last point, or the last restraint, is that we have to see the present signaling and transmission characteristics of the subscribers loops. Now, what is a subscribers loop? The subscribers loop is the pair of wires connecting a subscriber to the local serving switch or the local telephone exchange. And you might be knowing that the connectivity between a local exchange and a telephone set, it involves multiple points. From if we go from a telephone set to the telephone exchange, we can trace that from telephone exchange to a telephone set also. From the telephone exchange where a digital switch is connected, it is basically connected to the main distribution frame of the telephone exchange, and it is basically connected on the numbers side, which is also called the horizontal side. From the horizontal side, jumper wires are involved to connect that horizontal side to the vertical side. On the vertical side, primary cables are connected or terminated, and these primary cables are normally of 300, 600, 900, or even 1200 pairs. And these large cables, they go out into the main roads and streets and go to a cabinet or the curb that is installed, which looks like an almirah, and it is installed somewhere around the corner of your street. It is connected to the primary side of that cabinet. This primary cable is connected to the primary side of the cable. There is a secondary side of the cabinet also. The secondary side and the primary side are connected through jumper wires. From the secondary side of the cabinet, 100 pair cables come out, and they are distributed in different uh, areas and different streets, uh, uh, with 10 pairs each going to each distribution point which is installed on a pole. From that distribution point, which has, as you know, has 10 telephone exchange capacity, it is connected to uh, to a subscriber's premises through a drop wire. A drop wire, as I have already told, is normally of black color, and presently the drop wire that is being used right now, it has three wires. Two are copper wires which uh, which carry the signal, the baseband signal from the telephone exchange, coming from the telephone exchange to the subscriber, and the third wire is normally a steel wire, which is basically a strength member. Now this is then further connected the to the external rosette, which is installed outside a customer's premises. From this external rosette, a flexible wire, normally of a single pair or two pairs, it comes out and goes to the internal rosette. It is installed, it is terminated into it. From the internal rosette, a line cord which connects this internal rosette to the telephone set uh, with RJ11 connectors on both the sides, and after that there is the telephone set. So we should know what is the all the things that come in between a subscriber's loop. One important thing that a subscriber's loop provides is the talk battery for telephone transmitter. Actually, the whole telephone line from the telephone exchange to the telephone set, uh, it has minus 48 volts on it. And how do we get that minus 48 volts? From a DC power plant consisting of uh, batteries, a large battery bank which is placed in the telephone exchange. We need to have current to flow through the loop when the telephone instrument is taken out of the cradle, or it is done off hook. When it is off hook, we can also call it engaged. When you put it back on the cradle, it becomes disengaged. And when we engage it, or when we pick up the receiver set from the cradle, it tells the switch that an access is required, access is requested. So a line is seized by the switch, and the first thing that the first resource that that switch provides is normally a DTMF receiver. A DTMF receiver is a dual tone multi-frequency receiver, electronic system that allows you to dial a certain number, and it understands what number is dialed. There are two ways to dial a number. Number one, it can be tone dialed, which is normally you have seen which you have already seen in the older telephones, in which a round movement is done, and when you dial a certain number, for example 4 is dialed, it is it is moved, the dial is moved round up till uh, uh, an AND gate, and when you leave it 4 times, the system creates four pulses basically, because it makes and breaks a circuit 4 times. Similarly, we have the capacity of dialing 10 different numbers from 0, 1, 2, 3 up to 9 in that case. While in a DTMF system, which is also called a pulse, a tone system, we have normally uh, it is normally made in the form of 12 buttons, which are placed in 3 by 4 format, because or 4 by 3 format, because there are three rows, because there are 4 rows and 3 columns. And it is quite similar to your telephone, mobile phone also. If you see your mobile phone, just go to the dial pad. You'll see these are 12 different numbers: 1, 2, 3, 4, 5, 6, 7, 8, 9, star, 0, and hash. So to dial one number, we have to engage two different complete two different frequencies from two different sets. One on the rows side, we call it small f1, f2, f3, f4, and uh, on the column side, we would call it capital F1, capital F2, capital F3. So a combination of small f1 and small and capital F1 would give you 1, and so forth. In this way, it dials a number. And the first thing that a telephone exchange provides is the DTMF receiver, which understands the number that you are dialing. Now let's move forward. Here we have telephone battery source voltage, where the voltage is standardized to for minus 48 volts. The circuit is given. How do we know that the quality of the local speech connection is good or not? It is given by the loudness rating. Loudness rating is the main parameter for measurement of quality of speech. And there are basically two methods. We can have subjective or the objective methods. We can have the customer's opinion also, and we can have recommended values of loudness rating, and then we can determine the loudness rating. In this table you can see that if the loudness rating, overall loudness rating, is between 5 to 15, then more than 90% of the customers would say that the service is, or the quality of the voice is excellent, good or excellent, and only just over 1% would say that the quality is bad. But as the overall loudness rating increases, the people who like the service tend to decrease, and the people who hate the service tend to increase. So we should keep it to a minimum. Between 5 to 15 dBs is a good choice. Circuit noise has little contribution to the impairment, but we do have some problems with that. For example, if we have a crosstalk, that is a big problem, uh, because that would create a lot of problems for both the customers. This slide, in which it is explained what is the overall loudness rating. From a telephone set to the local exchange, the overall loss of signal, or loss of signal in dBs, is called the sender's loudness rating. From that exchange to the exchange at which we need to have the on which our destination is connected, we have the circuit loudness rating, and from that exchange to our destination or the desired telephone number, we have got the RLR, which is called the receiver loudness rating. If we add the sender's loudness rating, circuit's loudness rating, and the receiver's loudness rating, we get OLR, which is overall loudness rating. And the overall loudness rating should not increase more than 15 dBs. It should be around 5 to 15 dBs. That would give us a very good result. Here you can see that overall loudness rating is equal to sender's loudness rating plus circuit loudness rating plus receiver's loudness rating. The sensitivity of the telephone depends upon two things: microphone and the earphone. The subscriber's loop design, while saying what subscriber's loop design techniques we are going to use, first of all we need to see what is the critical parameter for it. The critical parameter is the distance d, which is between the telephone set and the telephone exchange or the switch itself. As D increases, the attenuation increases because the copper wires, they have their resistance, they have their impedance in between, which causes attenuation of the signal. There is a limit for D beyond which the local loop signaling may be affected, and in some cases the transmission may be affected. When we call transmission, it means the transmission of voice. When the telephone is off hook, there should be enough current flow to actuate the local switch where the loop terminates, so that it is able to understand what telephone number is being called, so that its DTMF receiver or the pulse receiver should understand the number dialed. Now, greater the diameter of the wire, attenuation per unit length would be less. An off-hook telephone exchange, uh, an off-hook telephone exchange will always show minus 48 volts all over the loop. Two important variables to determine, basically, as I've told, that uh, we need to see how can our signal go to the farthest end. There are two things that restrict our signal to go to the farthest ends. Number one, the maximum loop resistance. For example, a telephone exchange uh, can bear a maximum of loop resistance of 2400 ohms. That also in the case of older exchanges. In the newer exchanges, the telephone the the maximum loop resistance is approximately allowed maximum loop resistance is approximately 1300 ohms, out of which 300 ohms is for the telephone set itself. And the second thing that affects is the maximum attenuation in the loop. There are two ways to standardize this attenuation. The first one is the European standard, which takes 800 Hz as a standard signal, and it says that in the complete loop there should not be more than 6 dBs of attenuation at 800 Hz, while the US standard says that if we send a 1000 Hz signal over the loop, it should not undergo more than 9 dBs of attenuation. So we have got two different types of uh, uh, variables that determine the maximum length of the loop. The first one was the resistance, and the second one is the attenuation. Now let's see how does attenuation affect and how does the resistance affect. The resistance determines the maximum length of the subscriber's line. For example, 1300 ohms is the standard for the latest digital telephone exchanges, out of which 300 ohms is reserved for the telephone set and 1000 ohms is for the loop. Earlier exchanges could allow 1800 ohms and 2400 ohms also. But right now, since we do not need to have to send our signal to very far off places as we had to in earlier days, so um, we can have a 1300 ohms restriction, which is quite good. Also, the quality of the cables has improved, and we can send the signal to the farthest ends. And normally, what happens is that at certain distance, a new telephone exchange area is overlapping, so we can hand over those telephone exchanges to those telephone numbers to that new or the neighboring exchange. How can we calculate the resistance limits? DC loop resistance of copper conductors is RDC, which is the loop resistance in ohms per mile, and it is equal to 0.1095 divided by d square, where d is the diameter of the wire in inches. For example, if we find the diameter of the conductor wire, we have to find the diameter of conductor wire while it is a 10 miles loop with 1000 ohms limit. If this is the condition, then how can we find out the diameter of the conductor wire? RDC can be found by dividing the limit of resistance, which is 1000, divided by the length that has to be covered, which is 10 miles. So 1000 divided by 10 would give us 100 ohms per mile. This is RDC. Now, as you know from the equation that we learned in the previous slide, RDC is equal to 0.1095 divided by d square. Here we would find out that d is equal to 0.033 inches, which can also be called 0.76 millimeters, or we can say 0.8 approximately, 0.8 millimeters. Now this is a very important and interesting table that we are going to study right now, and I showed you there would be, if there are exams, that then I would definitely give some part from this table also, because I want you to know how to read a certain specification table and select the right value, or select the right cable that is available, or right gauge of the cable. Here normally the gauge that is used is the American wire gauge. Again, this is an example in which we have to calculate the maximum loop length of for 1000 ohms signaling resistance using 26 AWG gauge cable. In this table, you can see that we have got cable gauge given in American wire gauge. It goes from 28 to 26, 24, 22, 21. As we go down this gauge number, the diameter increases from 0.32 millimeter to 0.405 to 0.511 to 0.644 to 0.91. Now the next column gives you the loss in dBs per 1000 feet, and the fourth column gives you the loss in dBs per kilometer at 1000. Both of these are given at 1000 hertz, which is the American standard. The fifth and the sixth columns give you the loop resistance in ohms per 1000 feet and ohms per kilometer. This is a very important table that is used to find out the distance that can be covered while we are using a certain pair of wires, the distance covered by the signal, or if we have a signal and we have a certain gauge of wires, then we can find out the and we have a certain distance to cover, then we can find out the cable gauge in American wire gauge. And such would be the problem given in the exam. So the trick in this problem is that we need to know that if we get a certain value, for example 0.319, should we go for 22 American wire gauge? No, we cannot. we have to uh, go to the 19 American wire gauge. Just think about it and find out why did I say this. And this is a point to ponder, and this would be a part of your evaluation. Now the maximum loop length for 1000 ohm signaling resistance using 26 wire American wire gauge loop would be 1000 over 83.5. 83.5 is taken from the table given in the last slide. We get 11.97 kilo feet, 11 or 11,970 feet. Now, if we consider the older exchanges in which we have 2400 ohms switch, we can subtract 300 ohms for the telephone set. We are left with 2100 ohms to play with for the loop. Now, if we are using 26 American wire gauge conductors, then the distance would be 2100 divided by 83.5, and we get 25,149 feet, considerably more than double as compared to the latest exchanges. Now, another important point: signaling limit on the subscribers loop. When we are considering the signaling uh, of the telephone signals, for example, signaling includes the telephone number dialed, the numbers dialed, and the tones sent, and the telephone and the ringing current sent. All these are included in signaling. And what affects signaling? Resistance of the loop affects the signaling. So while designing a signaling and checking if the signaling is done properly, we need to check the resistance of the loop. And if we check the resistance, and if it is because it is no limiting factor in signaling, if that is checked, then then the loop loss in dBs will take care of itself. It would be okay. Now let's see what parameter should we see if we have to check the transmission. For example, we want to know if our signal, our voice signal would reach the other end from the telephone exchange to the telephone set. While checking for transmission limit, we need to check the attenuation. We do not need to check the resistance, because if the attenuation is within range, then resistance would already be checked and it would be okay. Attenuation of a wire depends on multiple factors. For example, its frequency, the frequency of the signal, resistance, inductance, capacitance, leakage, conductance. Resistance of a line depends on the temperature also. So the open wires attenuation may vary up to 12% between winters and summers. Variation is much less for buried cables, because it does not carry a lot of difference of temperature. Not much, not as much to change the resistance parameter. And this table, this is also a very important and interesting table, which shows you uh, the ratio of the attenuation. If the loss of the subscriber's loop is limited to 6 dBs, then the maximum permissible loop lengths are derived as follows. For a 28 American wire gauge cable, here, just a second. This 28 American wire gauge cable. We have 6 divided by 0.666. I've got this value of 0.666 from that very important table that we discussed earlier, and we get a value of 9 kilo feet. Similarly, for 26 we get 11.7. For 24 we get 14.7. As we go down, the diameter of the wire of the conductor is increasing, and the length to which this signal can be passed on, that increases also, while the number of the American wire gauge is decreasing from 28 to 26 to 24 to 22 and 19. It goes down while the distance it can cover, it can allow the uh, signal to cover, that increases considerably. Now there are multiple methods to increase the length to which a signal can be sent. Number one is we can use a conductor with higher diameter, or, uh, or a lower numbered wire gauge cable, but that incurs a lot of cost. So other way to do it is the use of amplifiers or range extenders. And the third way that has been used for quite a long time is the inductive loading. What happens is that there is a capacitance between the conductors carrying the signal, and the conductors going parallel with it, and between that conductor and the ground. To cater for this or counter this capacitance, we introduce an inductor at a certain distance. Uh, that in, that inductor would be of a certain value, certain a number of certain units of henries, and it would be placed as at certain distances, and it would counter the capacitance that has incurred due to the parallel cables going, or the due to the parallel conductors going along. So this would reduce the impedance, the overall impedance of the link, and would definitely increase the distance up, up to which a signal can go easily. So we need to have some coils. These are also called loading coils, which are basically inductors. Now, there is this particular standard about these loading coils, and they have got a code letter. For example, if it is a code letter A, it means that such a conductor would be placed 700 meters apart. After every 700 feet, after every 700 feet, or 213.5 meters, a new loading coil would be introduced, and after again 700 feet, a new there would be another loading coil, and so on and so forth. And you can see in other code letters, for example in E, you can see that you have to place the loading coil every 5,575 feet, right? So, and in the Y case, we have to place loading coil after every 2,130 feet, or 649.6 feet. 6 meters, right? Now, normally the code that is given in this case is, for example, 19H44 or 22B88 or 19H66. Here the letter H gives you the letter code that we have studied in the last slide. 19 means the gauge of the voice pair which is being loaded, and 44 means, for example, in the first case 19H44, 44 means the value of inductance which is given in millihenries. So this is a certain designation of the loading coils. You can see this in this table also. I would like you to uh, read this table and try to understand what it is doing. You can see in the first and second column we are using American wire gauge 26, which has a particular diameter of 0.405 millimeters, and the mutual capacitance of given in nanofarads per kilometer is 40 in each case. And if we do not use any type of loading which is given in the first row, and it says type of loading none, the loss in dBs per kilometer is 1.61, while if we include a coil loading or a loading coil of number H66, H as I've given you the table in the previous slides, that gives you the distance between two loading coils, and 66 is the amount of inductance given in millihenries. Then the loss in dBs per kilometer would be reduced to 1.25 as compared to 1.61 when we did not have any type of loading. So we can send our signal to farther places. Okay. For example, maximum loop current is 20 milliamperes, and each loading coil also adds 5.5 ohms. This is one of the negative sides of putting the uh, loading coil, but we need to see if our signal gets an extension of distance. For example, our signal goes uh, beyond its originally designed length, then putting a loading coil is okay. If we include a mini loading coil, it would add 8.5. Signaling is limited by the type of exchange and the diameter of the subscribers pairs, because the diameter is directly proportional to the resistance per kilometer or per unit length. Transmission is limited by the characteristics of the pair, which include the capacitance and the frequency and the resistance and the inductance in the loop. Both can be extended, but extensions cost money. If the pairs to be extended are few, do the extension by using pair extenders or amplifiers. If the pairs to be extended are in large number, then set up a new exchange or satellite exchange or an outside plant module. Nowadays, a very good example of such a module is an MSAG, which is multi-service access gateway, right? Now, what is a subscriber loop impedance? Characteristic impedance looking into the line circuit from two-wire switch is 900 ohms. It is also called the compromise impedance. 600 ohms is also considered to be a value of this impedance. The termination impedance at each of the 4-wire circuit are to be considered to be are also considered to be 600 ohms. Now we'll also talk about the 4-wire circuit and the 2-wire circuit and the conversion in between, or the hybrid transformer that converts a 4-wire system into 2-wire and a 2-wire into 4-wire. And why do we use a 4-wire system? Because we need to have two different loops for transmission and reception, so that we can put an amplifier on the transmission side separately and on the reception side separately. But to do that, we need to convert our 2-wire system on which our signaling is done to a 4-wire system primarily. Another value of 735 ohms, which is still another compromise like 600 and 900, is also used. Trunk plants which connect the two different exchanges normally use 22 American wire gauge cables. So the characteristic impedance approaches 600 ohms at 1000 Hertz. Loaded subscriber loops have Z0, or the impedance approaching 1200 ohms. Loaded means in which loading coils are introduced. Now the characteristic impedance may also be 135 ohms to 150 ohms at higher frequencies on the high-speed network. Now let's see how were previous loops designed, or the previous older subscriber loops designed. Before 1980, one of the following three loop design plans were used. The resistance design, uni-gauge design, long root design, and what we used to do was just a second. Now let's see what we do right now. We have revised resistance design. You can see the previous design in the book and in the presentation also. The loop resistance is for 0 to 18 kilo feet is 1300 at the maximum, which includes the resistance of cable and the load coils only. 18 to 24 kilo feet for 1500 ohms maximum, which includes the resistance of cable and load coils only, and greater than 24 kilo feet they use digital loop carrier. Similarly, in this way it is designed right now. And the second method is the concentration range extension with gain. In this case, loop resistance is considered from 0 to 2800, which includes only resistance of cable and load coils. And the load coils normally used are H88 for more than 15 kilo feet. And some more specifications are given below.